Hello, I'm Dorien Herremans. In this video, I'll talk about convolutional neural networks, a category of neural networks that have proven extremely efficient in tasks such as image classification and image recognition. But what makes CNNs so successful, and how are they different from traditional neural networks? In fact, CNNs share many common properties with traditional neural networks. They are both made up of neurons with weights and biases that are learned during training. Each neuron receives several inputs, takes a weighted sum over them, passes it through an activation function, and responds with an output. The network architecture has a loss function, and the fundamental inner workings are mostly the same for both CNNs and traditional neural networks. So how are CNNs different than neural networks? One of the most apparent differences is that CNNs operate over volumes. Unlike neural networks, where the input is a vector, here the input can be an image. In this video, we'll focus on the convolutional layer, the main building block of a convolutional neural network. Zooming in on this red area which represents the convolution, the following graph shows a very important feature, the kernel, also called the filter. Filters will activate when they detect specific features at certain spatial positions in the input. In order to properly understand filters and how convolution works, let's look at a very basic example, a filter for edge detection. To make things a bit more easy, let's take a grayscale image as an input. Grayscale only has one value or channel per pixel. On the left here, we have a 6x6 input image. In the center, we're going to apply a 3x3 filter. The filter in this example is focused on detecting vertical edges. Now, in order to do this, we start by convolving the filter over the image. This basically means that we take a sliding window and calculate the dot product of the window with the filter. This will give us a new matrix called the feature map or activation map. For the first window, taking the dot product means multiplying 3 by 1 plus 1 times 1 plus 2 times 1 plus 0 times 0 and so forth, which results in -5. This number we just fill in the feature map matrix. We do the same for the next window and so on using a sliding window approach. This will result in a complete feature map. Notice that this new matrix is a little bit smaller as it loses some information around the edges. In order to avoid this, the original input image is often padded, but we won't go into this in detail here. Now that we know how convolution works, let's make our example a little bit clearer and apply it to an image with a clear vertical border. The input image here has a clear line in the center as the left half is gray and the right half is white. After convolving the same filter as in the previous slide, we get high values in the center of the activation map, thus showing that the vertical edge is detected here. So in practice, backpropagation is used to learn weights of filters so that they can best perform the classification problem that the network is trying to solve. For instance, some filters might serve to flag horizontal edges, vertical or even diagonal edges. In the case of color images, because previously the examples I've shown have been of grayscale images, in the case of color images, filters can be used to detect certain color changes. The image on the slide shows some common filters that can be learned by convolutional neural networks. I hope you enjoyed this video and now better understand how convolution works, one of the key principles of convolutional neural networks.